today we'll discuss something knowledge presentation first about 1 hour and after a corporate from probabilistic inference as well.
Is your voice breaking, or I am having a weak signal? Participants, are you able to get his voice clearly?
Somebody please respond if my audio is clear.
No, your audio is breaking. In fact, earlier it was okay, but a little ago it was okay, but I don't know what happened.
Is it clear now?
Oh, it's better, I think so.
Okay. So maybe the earphones were the culprit. Okay.
Yeah. Thank you.
Yeah. Okay, fine. Thank you for the feedback. Yeah. So as we planned, we'll first cover the basics of knowledge representation and reasoning, what it is, why it is required in the big context of AI. And a part of it is probabilistic inference also. We will see why it is or how it is done. All right. So I would like this to be a interactive session. So feel free at any given point in time. I'm not really sure whether you can unmute yourself and ask questions. At least you try to respond when I take a pause for your response, whether it can be typing some things in the chat box or raising hand, something like that. Okay. And yeah, let's get started. So knowledge representation. What exactly is knowledge representation? So in the broad context of AI, right. So yesterday we have seen the search agents, right? So agents that plan the course of action, right? We have seen approaches like breadth first search, depth first search. Essentially, they were all looking to reach a goal state starting from an initial state with an objective in mind, right? So they are planning agents, and that part is okay. Now let's try to put all of this in a bigger picture. So what is knowledge representation? Essentially representing information which is useful about the real world in the context of AI agent is knowledge representation, right? So whatever information that is useful about the world that the AI agent is going to be deployed, right? That is knowledge representation. What is the aim of that? Basically, we shall conduct inferencing from the knowledge, right? Inferencing means trying to take some actions and trying to achieve a goal, right? We need information to be represented in a way that facilitates to perform this inferencing. So this is the broad idea. What is knowledge representation and why it is required? We need to essentially collect information from the real world and also to represent in a way that facilitates inferencing. For example, let's take a simple case where there are two variables, X and Y. There are different possibilities for the variables X and Y to have. For example, X can be 5 and Y can be 6. In a different scenario, X can be -2 and Y can be 4. And you can give another pair of values for X and Y and so on. There are infinitely many possibilities, right? These are all possible worlds. We sometimes call them models. Every one of them that is listed in the slide is a possibility, because our world has only two variables, X and Y. Because see, these words, world and model, are very tricky. Why I say they're tricky is basically this is only within the context of a particular AI agent and a particular task. Okay, if at all the AI agent is worried about only monitoring these variables and taking an action based on that, that is only our world. Okay, that is why typically these scenarios are referred to as worlds or models. Okay, but if somehow I have this knowledge about the world, which is X is greater than 4. Okay, this assertion is coming from my knowledge about the model or the world. Essentially, some of these models would be invalid. For example, X is equal to -2, Y is equal to 4, and X is equal to 4, Y is equal to -5. These will not be valid models anymore, right? Because we know some information about the world, which is X is greater than 4, right? So because of this information or assertion, we got to know a couple of models in this are not valid anymore, right? So essentially, we have some knowledge about the world and we need to represent it. And that should facilitate the AI agent to take some inference, to take some actions. So that is exactly what knowledge representation is. The key here is we don't know what is the language we should use to tell the AI agent all this information about the world, right? Whatever information that is there coming from the world, it has to really be fed into AI agent in a way that it consumes it and takes actions. And also, you can think of it as a programming language, for example. Very crudely, you can think of a programming language where it encodes all the worldly information and facilitates to take actions and inferences, essentially. For example, we use logic and probability. We will see examples for both. How do we actually use logic to encode all this information about the world so that the AI agent will understand this knowledge or information and tries to perform some reasoning to take some actions. Okay, probability is also one language to represent knowledge about the world, particularly in the AI context. So this slide would give you a broad taxonomy of knowledge representation. For example, the very basic thing, or very first kind of language for knowledge representation in the AI history is logic, right? We will see more details about logic, how we can use logic to encode information and how it facilitates to perform inference. And this is kind of a crude level of representing knowledge. And if you want more details about the world, like if you want to encode objects and also encode or represent the relations among the objects, that is also possible in a different language that is called first order logic or first predicate logic. And if you add another dimension to it, which is time, this evolves to be first order temporal logic. These are all different languages for representing knowledge, okay, in the AI agent. This is about logic, and this path which I am highlighting takes care of this logic path, where you have only true or false kind of variables for values for each variable. But the degree of belief can be non-binary, right? We will see examples. So please bear with me, even if it is not very clear, okay? So true or false is very binary, right? That is what logic deals with. All the variables either assume true or false. But some of the variables or some of the real world scenarios need to assume non-binary values, right? So for example, is it gonna rain today? Maybe or may not be. With some probability, I can say it may not rain, or with some probability, I can say it may rain, right? The belief here is not binary. So this kind of a language to represent the possibilities of the world or information about the world takes you to the probabilistic propositional logic, where we see Bayesian networks, one of the examples of encoding the knowledge and feeding it into AI agent to perform inference, right? So there is another way to represent the knowledge, which is fuzzy logic, where the degree of truth is also non-binary. For example, if I ask, am I tall? It depends, right? I cannot, or I can say I am tall. It may not be truth, or the truth value depends. For example, in a given geography, I may be tall, but if I am considered among a different geography or demography of another continent, per se, for example, I may not be tall there, right? So the statement I am tall or somebody else is tall is relative. The degree of truthness is variable, right? So if you consider that kind of a world encoding for worldly knowledge, that language is fuzzy logic. So historically, there were times where propositional logic dominated the field, fuzzy logic dominated for some more years in representing knowledge for AI tasks, right? So there were periods starting from 1950s, 60s, all the way to 2000s, early 2000s. There were prime times for each one of them. For example, early 2000s, probabilistic logic kind of ruled, where you saw the probabilistic graphical models and other derived models to be taking the limelight. Some time ago, fuzzy logic did that, and yeah, and very beginning, propositional logic has kind of started the knowledge representation thing in the first place, right? So the summary so far is knowledge representation is required to encode information that is useful about the world, and not only encode, but it should facilitate inferencing for an AI agent, right? So with this in mind, let's try to understand what are the differences. So differences probably we'll do it late. Okay, let's do it. So as I said, there are four or five different broad knowledge representation languages. For example, the propositional logic, ontological commitment, and epistemological commitment. Basically, these complex terms, don't get afraid. These are simply terms to represent the building blocks. For example, in logic, the building blocks are facts, and the values they can take are true, false, or unknown. On the other hand, first order logic, it represents the world. The building blocks to represent the information is facts, objects, and their relations. The world, information about it, can be represented in terms of objects and the relations among them, and they form sentences or assertions which can assume true, false, or unknown, right? You can see as you go down, the granularity of representation is increasing, right? So likewise, probability theory also has statements which are facts with a degree of belief, right? Which is probability. On the other hand, fuzzy logic has the building blocks as facts with degree of truthness also, right? Not only the belief, but the degree of truth can be variable. Okay. And the commitment from epistemological side is basically the known interval value for each of them, right? So given 1 hour or 2 hours of time for this module, it's really difficult to, take examples from all these things and go in detail. That's why I try to briefly make these things clearer while focusing on at least one of them. For example, propositional logic we will do, and also probability theory, Bayesian networks also will try to do, because they are kind of very important and they lasted relatively longer serving the AI waves. Okay. All right. Essentially, these are different languages to represent knowledge. What are, for example, think of programming languages. The instructions are given to computer using different constructs of the language, right? So similarly, you can think of these things as constructs. How the knowledge, how each one of these languages enables us to represent knowledge is what is different across all these languages, right? So let's try to understand why this kind of thing is required. So any AI agent that uses this kind of knowledge represented in some language is known as knowledge-based agent, because this agent is relying on this knowledge to act in the real world, to take inferences in the real world. The name is quite suggestive, knowledge-based agents, right? They use reasoning over an internal representation of knowledge. Because we are representing the knowledge for it, it will perform reasoning on the knowledge to take the best actions, right? And try to contrast it with the problem-solving agents, which were solving the search problems. Okay, their knowledge is very limited. They know only these things: what actions are available and what states will result if I take a particular action. Remember, these are what were available for the problem-solving agents. They don't know general facts. They don't know the general knowledge about the world. All that they know are what are the states available, what are the actions available, what will result if I take a specific action from a specific state, right? This was what they know, problem-solving agents. They don't really have other knowledge apart from this information. But on the other hand, knowledge-based agents do know some information, the general facts about the world, which it is going to be deployed. And based on that and other information, it will perform reasoning and takes the best action. Okay. All right. So the central component in all these knowledge-based agents is knowledge base, which is essentially a set of statements or sentences. So you can clearly see knowledge is represented in knowledge base. Within that, each of the statements will form the knowledge, right? So that is what we've been looking at. These sentences are expressed in a language known as knowledge representation language. We have seen 4 different or 5 different things. So each row in this table is one language. We can use propositional logic to represent these facts and knowledge, or we can use first order logic, or we can use probability theory to represent all this world information, so that the agent will consume it and takes the best action. So that is essentially knowledge-based agents. The central component is knowledge base, which is essentially a set of sentences which are expressed according to syntax and semantics. Each language has a different syntax and semantics, like any other programming language. Right. So let's take a closer look at knowledge base. Okay, so there are some sentences taken without being derived. Those are known as axioms. These are kind of truths taken for granted, right? So, for example, I'll say birds can fly. It is not derived. We are starting from that sentence. This is an axiom. Birds can fly because they have wings, they fly. These kind of statements are not derived, rather they are axioms where we start deriving from that sentence. Okay, this also is part of knowledge base, KB, right? And knowledge base facilitates adding sentences, that is called adding new sentences or new information to the knowledge base. Also, you can query a knowledge base about something, whether this is there with you, or is this possible, is this derived, is it possible to derive some statement from whatever knowledge we have already in the knowledge base. If yes, you will derive it and then add it to the knowledge base, increasing your knowledge, right? So these are the common properties of a knowledge base. It should be able to provide a facility for adding new sentences, and also to query what is already known about a particular variable. Okay, so this is broadly about knowledge representation and knowledge-based agents. Where you want to realize a knowledge-based agents, you need to have a knowledge base, and the knowledge base essentially is a set of sentences that can represent the world information in a specific syntax and semantics. Each language, based on the language, will have a different syntax and semantics. Okay, now let's look at logical reasoning, and I'll try to introduce some fundamentals about logical reasoning. Every one of us mostly know all these things, so I'll try to quickly revise what are the important fundamentals that we need. So the fundamental of logical reasoning is conclusion would be correct if the available information is correct. If you are starting from all the right information, and if you take sound inferences, which are supposed to give the right conclusions, right? So this is the fundamental behind logical reasoning. Start with right information, you will conclude with the right inferences. Okay, so let's try to see how the logical reasoning represents KB. Okay, so KB consists of sentences expressed according to a predefined syntax. For example, x plus y is equal to 4 is a very well-formed mathematical sentence, whereas x4 y plus c is, it's really not a well-formed sentence, right? So there is syntax. Clearly, your sentences need to have the predefined syntax to make sense, essentially. This is, you can relate easily to a programming language that has a syntax to represent any sentence, right? And logic must also define semantics. Semantics meaning the meaning of a sentence. There has to be meaning for a sentence. For example, take this. What is the meaning of this? Plus has a meaning, which means the quantity on the left and the quantity on the right are mathematically added, and is equal to also has a meaning. It has a semantics. What is it? The thing on the left and thing on the right are equal, are equivalent, right? So this kind of semantic, it carries a semantics. Because of the meaning, we would be able to assign possible true or false value given the world conditions. That means given we know x and y values, we can assign a truth value because we know it has a meaning. Plus has a meaning is equal to has a meaning. Now we can decide whether it is true statement or a false statement. Essentially, it should have the syntax and the semantics, right? So that is how you represent information about the real world, right? As I said, possible world, we know we refer to it as a model or a world, right? So let's take this sentence. If a sentence alpha is true in a model M, we say that M satisfies alpha, or sometimes M is a model of alpha, right? So this is just a terminology. So just we need to have some terminology with us before we actually get into the logic, the first language, actually. Yeah, predicate logic. Yeah. So there is another concept called as logical entailment, right? A sentence follows logically from another sentence. For example, the statement here says alpha gives rise to beta. So alpha entails beta. So what does it mean? Alpha entails beta if and only if all the models of alpha are a subset of all the models of beta, right? So capital M of B is this, we said satisfying, right? So capital M of alpha is the notation to mean the set of all models that satisfy alpha. Okay, so this is you try to understand this as a implies statement. Alpha implies beta. That means wherever models alpha holds, beta also holds, right? So that is what it means, right? So all this is required. Again, please bear with me. These are very simple, seemingly boring concepts, but these are the foundations to represent the knowledge and also enable the AI agent to conduct inference on top of this world knowledge. Okay. So inference algorithm is some tool that can derive things from knowledge base. For example, we will see one of the inference algorithms also. So let's say I is an algorithm which looks at the information in KB. Using that information, it derives alpha, another thing, right? Obviously, that is what we are after, right? We have to utilize the information present in KB. We, in the sense, the AI agent has to utilize the information in KB and apply these inference algorithms to draw new inferences so that you can take an action to maximize some performance, right? So yeah, slides and all would be provided, not a problem. Yeah. So if at all an algorithm I looks at the sentences and consumes the information to derive something new, you can represent like this. In I is inferring alpha from the given knowledge base, right? So this is essentially notation. So an inference algorithm that derives only entailed sentences is called sound inference algorithm or truth preserving. What it means is if an algorithm, a tool, is deriving sentences that are entailed sentences, that means alpha gives rise to beta, right? It is clearly deriving sentences from the knowledge base because they are logical, right? If that is the case, this algorithm is referred to as sound algorithm because whatever it is deriving is logically correct. That is why it is also known as truth preserving, right? So this is very, very sound. There won't be any logical error if you follow this algorithm because it is clearly deriving sentences that are logically entailed, right? For example, let me give an example. The knowledge base says all birds can fly, and a new information comes. Eagle is a bird. It adds to the knowledge base and it processes both these sentences. All birds can fly. Eagle is a bird. So it derives eagle can fly. It is clearly entailing from both sentence 1 and sentence 2, right? All birds can fly. Eagle is a bird. So eagle should fly. So this sort of an algorithm which derives only entailed sentences is known as sound algorithm because it will never derive something false, right? Because of that, it is known as sound or truth preserving algorithm, inference algorithm. Right. So there is another property which is known as completeness. An algorithm, inference algorithm. Inference algorithm means which processes the knowledge base and tries to derive new knowledge. That is essentially what is AI about, right? You try to understand the information about the world in the form of knowledge base or KB and try to run some inference algorithms to derive more information from what is known already, right? If such an algorithm can derive every sentence that is entailed, then it is called complete, because it is deriving every possible entailing statements from what is known already. That is meaning of completeness for an algorithm, right? For example, some algorithms will derive all the entailed statements, but not all the statements derived by an algorithm can be entailed statements, but if at all it is missing some of the entailed statements, it is not complete, although it is truth preserving, because, for example, there are 10 possible sentences that can be derived. An algorithm derives only 5 of them. It is sound because all the 5 are true, but it is missing another 5, right? So it cannot be complete. But on the other hand, if there is an algorithm which can derive every possible entailed statements, then it is called complete. Okay, so we essentially look for complete and truth preserving. We should get everything that is entailed. Then in that case, we will have maximum derivation possible, right? These are all theoretical properties for an inference algorithm to have. Okay, so this is how theory over AI developed, because before we start to realize, we need to understand what we are looking for, right? That is essentially motivation behind all this development of theory. Okay, so with this background, very brief background about the logical reasoning, we'll now introduce the propositional logic, the first programming language you can think of to encode knowledge to an AI agent. Okay, so how does so far, if you have any questions, please feel free to put them in the chat box. I'll quickly summarize what we have done so far. Okay, so we understood what is knowledge representation. Essentially, it is one way to represent knowledge about the world for an AI agent, because it has to consume it and perform some inferences over it to make to take some useful actions towards maximizing some performance or achieving a task, etc. Because it has to really derive from the knowledge of the world, right? So that is what is knowledge representation. There are multiple different ways to represent knowledge. For example, propositional logic, first order logic, probability theory, fuzzy logic, all these are different ways of representing knowledge to an AI agent. What differs? The way we represent knowledge differs across all these things. For example, propositional logic is the simplest one, where you have sentences with associated truth value, true, false. And probability based knowledge representation uses same things, but there is a value associated with each of these statements, right? Probability, obviously. And if you add time also, it little bit complicates, and it is called objects and relations you can add. It's kind of adding more and more granularity. From propositional, you go to first order logic, and you can further go down by adding time domain. It makes temporal first order logic, etc., etc. Okay, so as I said, it's a historical development starting from propositional logic. So let's try to understand one of them. Yeah, so one question is, can we give brief examples to understand? Okay, for example, so in propositional logic, a sentence is taken as an atomic module. For example, Rama and Lakshman are brothers. Okay, so two objects, Rama, Lakshmana. So in propositional logic, all the sentence will have a truth value, true or false. But if you want to represent this in first order logic, you have to divide this also into objects, two objects, Rama and Lakshmana, and there is a relation between these two objects. Is brother of, is the relation, right? So now you represent these two objects with this relation between them. Sometimes objects and attributes would be there. The table is of red color. Table is the object. Being of red color is the property. So now you have to represent using an object and an associated property, right? This is going another level beyond sentence, right? Breaking the sentence also and representing the individual modules with different things, right? So this is this will facilitate a little more because you are now into a different level, right? So you can instantiate different worldly objects into and then describe their relations also, right? I hope I have given an easy to understand example. Essentially, it is the granularity with which you want to represent the world knowledge to an AI agent. So there are limitations and advantages also. Right, there are definitely higher order things. You're right. Yeah, based on how granular you want to get into the details of representation, obviously. Yeah, right. So in the interest of time, I'll take now all of you into propositional logic. Right. So what is the syntax? As we said, every language of knowledge representation needs a syntax and semantics, right? So the syntax here defines all the allowable sentences. What sentences are allowed? How do we represent sentences? What syntax is this? So there are two types of sentences, atomic sentence and complex sentence. Atomic sentence is also known as propositional symbol. For example, all atomic sentences consist of a single propositional symbol. Symbol stands for a proposition that can either be true or false. For example, W13. That means something, okay, I'll introduce the Wumpus problem anyway. So my office is facing east, right? So that can be a statement, that can be an atomic sentence. My office faces east, right? P, capital P is a symbol that can be associated with either true or false value. You can think of this as a condition. So W13, I'll get into that example. Or I'm not really sure. No, Wumpus example was not covered yesterday. So okay, I'll introduce you to that. Any sentence that can be associated with true or false is the atomic sentence, single sentence. For example, as I said, my office faces east. That can be true or false, right? As I said, this language has two fixed symbols, true and false also. Now think of additive identity and multiplicative identity in mathematics. In algebra, we have 0. When you add anything to 0, the value is the same, doesn't change. Similarly, when you multiply something with 1, the value doesn't change, right? So something like that, you need to have some equivalence. Here also, true and false. So I am assuming every one of you know the digital logic, from where you can see conjunction and disjunction, and logical and logical or. If you have P, and then if you logically end with true, essentially it will be P. On the other hand, if you have P and logically or with false, it will be P only, right? So this is, you can see the analogy from math. You can take and see the necessity of having these things. Okay. And this is the syntax of the language. What we are discussing now is the syntax of the language, which is propositional logic. So that about simple statement or atomic statement. And there can be complex sentences also. Complex sentences are constructed from simple ones by joining multiple such sentences. And you need parentheses and some operators to join it also. So that is where we see all these operators come in. The negation, conjunction. Conjunction is logical and operator, because you're essentially dealing with binary variables or Boolean variables, you can think of them. So disjunction is the logical or, where you try to join multiple simple or atomic sentences to form a complex sentence. So implication is the conditional thing. If then, right? By conditional is if and only if. Left side implies right side implies left side. That is biconditional connection between two atomic sentences. Right. So these are the typical very well-known logical operators. Here in predicate logic, they work as connectives to form complex sentences. Right. So you want to represent some condition in the real world, which is not a atomic thing. So you need to represent using these sentences, this syntax, these connectives, right? So essentially, the summary syntax summary of predicate logic looks like this. So sentences, there can be atomic sentences or complex sentences. Atomic sentences have true, false associated with it, and the values true and false also, as I said, the multiplicative and additive identity equivalents here would be the conjunctive and disjunctive equivalents, true and false. Along with that, you can have literals like P, Q, R to represent atomic sentences. Complex sentences essentially are formed out of atomic sentences using these connectors: conjunction, disjunction, implication, and bicondition. Okay, so the operator precedence also is clearly defined. Again, think of any programming language where different operators are there and there is a clear priority given. Here also, operator precedence is clearly defined like this. The negation takes the highest precedence, and conjunction, disjunction, implication, and then the biconditional. Right. So this is a very clear description of the syntax of predicate logic. Right. So now let's talk about semantics. What is semantics of a language? This defines the rules for determining the truth of a sentence. Can be true or false, but we need to be able to understand to associate that value. So that is where semantics come into picture, right? So, for example, so one of the models or a real world situation simply sets truth values for every proposition or a symbol that is there. So this, given this kind of a scenario, any complex sentence can be derived, the truth value for that sentence can be derived based on the syntax. Okay, that seems to be. Yeah. So Sahit, yes, you're right. You can say it is associated with, yes, maths reasoning. Essentially, what we are doing is logical reasoning. These fields overlap very much. You're right. Right. So you need to understand semantics also. How do we understand the meaning of a given sentence in order to associate a truth value, true or false, right? So we must specify how to compute the truth value. That is semantics. So let's say the two sentences, atomic sentences, true and false. It is very clear. True contains the truth value true, false contains the truth value false. What about other proposition symbols? It comes from the model. For example, you need to understand and you need to know what individual sentences carry, whether true or false. If you know this, any complex sentence, you can assign the truth value whether true or false, because you know the meanings of these guys, right? How the conjunction, disjunction, and or operators work like, right? If two sentences are joined with an and, you need to have both true in order to have the complete sentence to be true, right? So that is the semantics. What is the meaning of and? That is the semantics of and. What is the meaning of conjunction or disjunction? So essentially, we are looking at truth tables for each of these operators, right? Defining truth tables and letting you know the meaning of the complex sentence. That is semantics, right? Semantics, as I said, I'm repeating more number of times because quite often a lot of students get confused. What do we mean by semantics? Semantics is the thing with which we assign truth value, essentially with which we understand the language. Given a sentence, how do we understand it? There is a semantics. For example, A conjunction B. How do I understand it? This complex sentence would be true only if both of them are true. That is the semantics I should understand when I see the conjunction in the sentence. Similarly, disjunction also. When does this hold true? At least one of them, if it is true, then the whole complex sentence is true. How did I know? Because I know the semantics. I know the meaning of the disjunction here, right? That is semantics. All right. Now we know the syntax and the semantics, right? Essentially, knowing the truth tables for all these operators and then precedence of all these operators is the syntax, right? Now you can derive truth value for any complex sentence that uses any of these operators, right? So that is essentially syntax, right? For example, as I said, negation of P is true if and only if P is false, right? That is how I understand negation of P. The meaning of negation of P is P would be true only if negation of P is true if only if P is false. Similarly, P conjunction Q is true if and only if both P and Q are true. In any model, in any real world, for example, you're looking at a specific world conditions. If P and Q both are true, in that specific situation, P conjunction Q would also be true, right? So that is the meaning or semantics of every construct in the language in this predicate logic, right? Also, P implies Q is true when except one condition where P is true, Q is false. Except this condition, every other possibility is true. Because there are two variables and each of them can take two values, there are four possibilities in total, out of which only one is false. The rest of the three are true, right? So this also is simple if and then logical operator. Okay. So this is if and only if, or sometimes it's called biconditional operator. This is true if and only if P and Q are both true or both false simultaneously. Only then this complex sentence is true. So this is the complete semantics of predicate logic. Okay. So essentially it can be represented with this simple truth table, right? So we all know this truth table. Given two atomic sentences, they can take either true or false, and negation would be true only if that is false, and otherwise it is false, right? Similarly, conjunction is true only when both of them are true. Disjunction is false only when both of them are false, except that everything else is true. And P implies Q and P, if and only if Q, are also very familiar to us. So this is the only condition where P implies Q is false. And similarly, if you see biconditional operator P between P and Q, if both false, it is true, or if both true, it is true. If only one of them is true, it is false. This is simple but very powerful syntax or semantics for predicate logic. Okay. Right. Now let's try to understand. We now understood the basics of a language to represent information about a world to an AI agent. So this is a simple predicate logic where there are sentences that are atomic, over which you can create complex sentences, and there is clearly defined syntax and semantics to derive truth value for any of the sentences using this truth table. Okay, so with this as our tool, let's try to represent one problem, one world. So there is this famous problem called Wumpus world, where it's a simple kind of a video game you can think of. The objective here is there are 16 cells. Each of them you can think of as rooms in a cave. Okay, so you are going after finding a gold. One of the rooms contains gold. So the objective of the game is to find the gold. Okay, but there are some challenges. There are some rooms where there are some endless pits. If the player enters any of that room, it's a closure of that. It's an end to the game, because you will be going into the pit. It's kind of game is over for you. Okay, and another challenge is there is a Wumpus. Think of a monster. Okay, so when you enter unknowingly that room, or knowingly, it will eat you away, the player away. That is also another way to end the game. Not a desirable thing, right? So you will be killed essentially. So this is the game. You need to go find the room where the gold is there, kind of a treasure hunt. But the catch is some of the rooms have pits. If you enter them, you will be gone. And there is another mishap which can happen is the monster is there. Wumpus is the name of the thing is called Wumpus. When you enter that room also, you will be gone. But there are some clues. For example, if one of the pits has the pit, one of the rooms has pit, the adjacent rooms will have a breeze, because it is an endless pit. The air will be flowing through it. So you can sense the breeze in the adjacent rooms. For example, 3,1. If this has pit, 2,1, 4,1, and 3,2. These will have slight breeze going through the rooms. So that is one indication. You can say that there is a pit in adjacent to any of the rooms with breeze. Okay, and another clue is if the Wumpus or the monster is there in one of the cells or rooms, the adjacent rooms will get stench, a bad odor. Okay, so if you sense in any of the rooms a bad odor, one of the adjacent rooms has this monster. Okay, so that is another clue you can sense. The AI agent which is playing the game will be able to sense it and derive that the adjacent room, in the adjacent one of the adjacent rooms, there is this wumpus, so I need to avoid it. Okay, another hint is when you enter the room with gold, you will see the glittering, the gold glitters, right? So that kind of glitter you can sense, and that is an indication that that is the room where gold is there. You kind of reached the goal. Okay, so this looks like a slightly complex problem, but it has a lot of useful information also about the world to be able to understand where you should go, the AI agent should navigate, where it should avoid going. Okay, so I hope everyone understood the problem. The objective is to find the gold. You can only move one step at a time, and also you move only non-diagonal directions, left, right, top, bottom. Okay, not the diagonal. And similarly, whenever I say adjacent, it is only the XY axis, not the diagonal axis. Okay, with all this thing, now let's try to represent this knowledge. Whatever knowledge I said, what is the knowledge I have? Whenever there is a pit in one of the rooms, the adjacent rooms will have a breeze. Also, whenever there is wumpus in one of the rooms, the adjacent rooms will stink or there is stench. Also, if a room has glitter, that means it has gold. This is all worldly information. We know this. And now with this information, we need to solve this puzzle of finding the gold. Which room has the gold? Okay. Again, so this problem comes again and again. So in case the problem is not very clear, stop me right now. Otherwise, we'll proceed. Okay. So now, how do we represent this world knowledge using predicate logic? What do we know? We know syntax and semantics. Syntax, there are sentences that are atomic, there are sentences that are complex. Right? For example, p x comma y is true if there is a pit in x comma y. I am representing p x comma y to mean that there is a pit in x comma y. This can be true or false. Okay. And again, w x comma y is true if there is a wumpus in x comma y. Okay, this variable w x comma y mean there is a wumpus in the cell x comma y. B x comma y to represent there is breeze in the cell x comma y. And sx comma y is to represent there is stench in the cell x comma y. Similarly, lx comma y is true if the agent is in the location x comma y. These are my variables to represent different knowledge about the world. Okay, for example, so again, knowledge base is set of sentences. I need to represent all this knowledge in a set of sentences. Okay, now can somebody tell me, if I'm starting my position, the AI agent is starting from here, what can be the starting sentences in my KB? Okay, so please try to respond as briefly as possible in the chat box. If I am starting in 1, 1, 1, 1, I am starting here. What can I have in my knowledge base? What information is available at this point in time? Change direction if S or B is true. Right, breeze and stretch. Right. So Shreyans, you're right. So because the AI algorithm is starting from 1, 1, obviously there is no pit in that location. If there is pit, obviously the game ends immediately. So there is no pit there. And also the very first information is my current location is 1, 1. That means L 1, 1 is equal to true. Because remember, how did we represent? L x comma y is true if the agent is in the location x comma y. Okay. Now, we don't know anything about 2, 1 or 1, 2. right? We have not entered that room 1,2 or 2,1. So at this point in time, we cannot say anything about having breeze in 2,1 or having stench in 1,2, right? That information is not known, but we know this much. Whenever there is breeze in current location, one of the adjacent locations has pit. That is some information we know. Whenever there is stench in my current location, there is wumpus in one of the adjacent locations. Okay, that information has to be encoded. This is general facts, right? You remember the search agents did not have this information, right? This is the privilege of knowledge-based agents, which can represent the general facts about the world. For this problem, world is only this cave that has 16 cells, right? This is the world for this problem. And there are different possibilities in this world. Some of the rooms have breeze, some of the rooms have pit, some of the rooms have wumpus, only one, in fact. And one of the rooms has gold, right? There is variation within the world also. Which room has what? You can permutate all these things. That way you can create different worlds. This is one particular instantiation, what you are looking at the screen. Okay. So the general information of having stench, if there is an adjacent location, if there is a wumpus in adjacent location, or having a breeze in the current location, if there is a pit in one of the adjacent locations. That is a general world knowledge you can represent. Before you start playing the game, you can represent that thing in the knowledge base. Let's see, how do we represent? Okay, so because number 1,1 location is the starting point, obviously there is no pit. So how do we represent that information? My first sentence is going to be there is no pit in 1,1. Negation of P11 is true. So all my sentences in the KB has pit true. So I'm representing with a negation. Okay. And also a square is breezy if and only if there is a pit in the neighboring square. This is a general knowledge about the world. This has to be told for every sentence, every square. Sorry about this. World knowledge has to be encoded for every square. For example, because I am in 111, cell 11, and I didn't sense breeze, I need to understand that the neighboring cells do not have pit. Okay, how do I start all this business? First, I need to represent, if at all there is a breeze, that means the neighboring ones have pit. See, that is how we represent using the constructs of the language, right? There is breeze in 1,1, if and only if there is a pit in either 1,2 or 2,1, right? This is how we use syntax and semantics to represent the knowledge. Okay, I hope all of you are following. The knowledge that was stated in English language needs to be encoded in the logic using the predicate logic, right? What do we have? All that we have is the syntax and semantics. If you understand syntax and semantics, almost anything can be represented in the language, the predicate logic language. So that is exactly what is happening. If at all there is breeze in 1,1, that means there has to be a pit in either 1,2 or 2,1, because if you are standing in 1,1, what are the neighboring things? 2,1 and 1,2. So that is what I encoded. 2,1 or 1,2. One of them should have pit. So this I will put in the knowledge base as my second sentence. This has to be done for every sentence because this is generally true, right? And also, what did I do? I did not sense any breeze in 1,1 because if you look at the world, clearly there is no breeze, right? There is no stench, there is no breeze in 1,1. Where the agent is currently standing, there is no breeze. Okay. So if at all breeze, one of them have pits, but I know there is no breeze. So what do I know? None of them have pit. There are two, P1,2 and 2,1. Both of them do not have pit. If at all they have a pit, I should sense breeze. Because I did not sense breeze, I can infer that there is no pit in either 1,2 or 2,1. So this is how an AI agent can understand the knowledge and draw inferences. R2 and R3 clearly will give rise to, because you need to refer to the truth table. Okay, truth table of this biconditional relation. So when one of them is false, the other one also has to be false, right? Only then the sentence is true. The complex sentence is true. Okay. So look at this sentence. This is false. What I am highlighting is false. That means both of them have to be false because this is a disjunction, sorry. Right? This is a logical OR, right? For this whole sentence to be false, both the individual sentences have to be false. That means no pit in 1, 2, no pit in 2, 1. So it can add these two sentences to the knowledge base. This is derived knowledge, right? This we are good at it. Humans are really good at logical reasoning. Our intelligence is like that. That is what we've done almost effortlessly, right? Now what we are trying to do is to build algorithms that can infer this kind of new knowledge from the known knowledge. So that is where the effectiveness of knowledge-based agents depend on. Okay, so let's just go further. We also know another fact. If at all a particular cell is stingy, that means one of the adjacent cells hosts the wumpus, right? So, but fortunately, we did not sense any stench in 1, 1, right? I need to represent that for 1, 1, right? This sentence that is stated in English needs to be encoded using the syntax and semantics of the propositional logic. This is what it translates to, right? A square is stenchy if and if there is wumpus in a neighboring square. So there is wumpus in a cell x, y. We can represent using w x, y. Okay, so we are talking about 1, 1. So 2, 1 and 1, 2 will be the neighboring. And if at all there is this true, this complex sentence to be true. But as I said, no stench in 1, 1. You can draw inference saying that there is no wumpus in either 1, 2 or 2, 1. Both of them do not have the wumpus. How do I know? Because there is no stench where I'm standing. Okay. Again, you have to keep this puzzle in mind because you don't have stench here, either 1, 2 or 2, 1. Right? Both of them do not have wumpus. This is how you acquire knowledge and derive knowledge. Okay. So you go on doing this again and again. Okay. Let's say now because I derived that 1, 2 and 2, 1, both of them do not have pit. Both of them do not have wumpus. So I can take one step towards my right or towards my top. Okay. So either this motion or this motion is safe. Why safe? Clearly there is no pit. Clearly there is no wumpus. That is why one of them is safe. So let's say I take this action. I move towards my right. Okay. 1, 1, 2, 2, 1. I moved here. So this cell. So what do I sense now? The moment I entered this cell, what do I sense? Or the AI agent sense? There is breeze. Yes, clearly there is breeze. Now, so how do we represent that? So I need to apply my knowledge about breeze. If at all there is a breeze here, one of the neighboring cells has pit. So what will be my neighboring cells here? For 2, 1, my neighboring cells are 1, 1, 3, 1 and 2, 2. Remember, not diagonally, only x-axis, y-axis are my adjacent directions. Okay, 1, 1, 3, 1 and 2, 2. So that is what I represented. If I sense a breeze here, one of these cells has pit. Okay, now I need to add that there is breeze in 2, 1 because the moment I go there, I can sense breeze. So I updated my knowledge. Remember, my sentences are growing. R1, R2, R3, R4, R5, R6. Now I have R7 because every time I have new information, I'll update my KB. Remember, the KB should facilitate adding new information and also facilitate to query it about something very specific. Okay, so these are possible if you design the knowledge base like that. Okay, right. So now I am including that there is breeze in this. So what do I understand? One of these cells will have pit. Clearly 1, 1 doesn't have any pit because that is where I started from, right? It has to strike off P11 because that is where it started. So only either 2, 2 or 3, 1 has pit. Okay, 2, 2 or 3, 1. One of them has pit. So the obviously, what is the safe option now? Which direction the agent should move? Yes, 1 is the only safe option, right? Remember, the possible actions are to move towards right or left or top or bottom. Clearly, it cannot go bottom. There is no bottom. And clearly, if you go to top, there may be a possibility for a pit. Towards right also, there may be a possibility of pit. So it has to get back to 1 and try exploring the other direction, 1 2, right? It has labeled 1 2 also okay. There was no pit or no wumpus, so it will try exploring the other direction, which is going in 1 2, right? I'm now stopping. This is only an example to illustrate how we can represent the knowledge using the propositional logic, and also how we can run inferences. So whatever inferences we have derived using our own intelligence, right? But if you want the AI agent to do this inference, you need to provide an algorithm, right? So Ajay, what is your question? Agent can move back also? Yes, yes, it can move back. The possible moves are left, right, top, bottom, right? So at this position, 2, 1, right? Yeah, you're convinced. Okay. All right. The point I was making is, as humans, we somehow get this knowledge very, very effortlessly. This inferring intelligence is, we are blessed in that way. But an AI agent should have algorithmic intelligence to perform this kind of inference over the known facts. Okay. That is where the inference procedures have to be built on top of this knowledge base. Okay. I hope I have convinced you that it is possible to represent the world knowledge using this kind of the syntax and semantics provided in this the first language that we have seen, right? Cool. All right. So now the next step obviously is to go ahead and try building some inference procedures. Given these sentences, how do we derive? For example, can I build an algorithm which can infer the pit in P12? Because we humans can do this logical reasoning and we performed automatically, but is there an algorithm that can give me there is no pit in 1, 2? Because we didn't sense any breeze. So how do we algorithmically get to these conclusions? So you can ask this question, right? Because you want to understand whether you can move to P12, right? So again, so how do we do this? You are starting here. Now the question is whether you can move to P2, 1. You have to ask your knowledge base that, can I go to P2, 1? Or is it safe to go to P21? How do we say? If there is no pit, if there is no wumpus, it is safe. So that is what you want to ask. Is it true? P12. That means, is there a pit in 1, 2? If you ask the knowledge base, it should be able to derive and say true or false. That is a simple inference algorithm we are looking for. How do we know? So a simple inference is, from whatever knowledge you have, you can try to build the truth table, right? And see what will happen. What values of P are valid, what values of P12 are not valid. That analysis you can make. For example, if I assign all the truth values that are possible to all the sentences that are there in my KB. For example, I know B11, B21, P11, everything, right? If I simply assign all the possible values, there are 7, 2 raised to 7 would be 128 possible models. And only some of them will hold in my KB, in my knowledge base. You look at all of them and see, we are looking at P21, right? All these cases, P21 is false. So that means P21 is false. Only that is only possible value for the current world, current knowledge. It is consistent with only having false value to that particular variable. Okay. This is a simple inference algorithm. You can try, work it out. Okay. So even please bear with me if it is not very clear. What I am trying to clearly say is, if you want to understand what values are taken for a particular value, particular variable, in this case P21, you try to elaborate using a simple truth table, try to assign all possible values and see what values KB will have. Okay, so those subset which have true, which is possible for KB, you try to see whether this to be possible, is there consistent values assigned to P21 or inconsistent values assigned to P21? Okay, so if there is something consistent, then that is the value it will take, and you can infer that value to the variable. Okay, all right. So that's a very simple thing, but it doesn't work out because the number of variables will grow and the truth table would be exploding. And in real world problems, it is definitely not possible with so much of information, so many variables. You cannot do this. We need a little more efficient algorithms. Okay, so there are a lot of theory developed on top of this syntax and semantics. So I'll quickly go through again. So I want to give you a very broad understanding of what is there. So that is why I'm trying to rush through. Okay, so please refer to the slides and also reading material later. But in the interest of time, I'm just going a little faster. Okay, so there are a lot of theory to prove logical equivalence. When do two statements equal?
Dr. Konda Reddy, would you like to give a brief break?
Yes, ma'am. Yes.
This,
really. Thanks for stopping. Yeah.
It's almost 4:40, 4:39.
Yes.
So we can meet after 5 minutes or so.
Excellent. Yeah. That's
so that participants also have enough time to think about the questions and they can come to you. Thank you.
Excellent. Yeah.
And a little rest to you also. Thank you.
Yes. Definitely, ma'am. Thank you, ma'am. Yeah. So as per the suggestion, probably we'll get back in 5 minutes, and please stay tuned, and thank you. And instantly, right, Rohan, you followed the answer. 1-1 is safe because you are not dead in 1-1. There is no wumpus, there is no pit. So the instantaneous reward, the reward it carries for death is, let's say, -1,000. For reaching the goal is +1,000, but any other intermediate safe things is +1. Okay, so the reward value, which is a variable all the way when you are playing the game, or the AI agent is playing the game, that is what it tells whether it is in safe or it is in danger, things like that. Okay. So think of a variable called reward, where in 1,1 your reward is neither 1,000 nor -1,000. That means you didn't reach the goal, or you didn't die. Manu, we are in 2-1, but we sensed breeze. See here, 2-1, there is breeze. That means one of these adjacent cells adjacent to 2-1 is 1-1, 3-1, and 2-2. One of them is having a pit, 2-2 or 3-1. Because we suspect that there is a pit, we don't move to 2-2 or 3-1. You see the breeze. When do we have breeze? If one of the adjacent things will have pit, then we get breeze here. Because the agent sensed breeze, it understood either 1-1 or 3-1 or 2-2 has pit. That is why, but 1-1 clearly there is no pit, because it started from 1-1 and it sensed no pit there. So one of these two only will have pit. So it won't go to 2-2, it won't go to 3-1. It will go to 1-1. Hope this is clear. Just give me 1 minute. I'll fill my water bottle and get back. All right. So the remaining questions probably will take towards the end. I'm really sorry. In the interest of time, let's just proceed. So basically, I hope I convinced you that the logic we have seen is fairly good to represent the worldly knowledge, and also I suggest you to go through the rest of the slides and also a lot of reference materials that I'll provide that can help you understand, help you build also to build inference algorithms which can be proved to be complete and sound also, right? For example, very simple inference procedures like if your knowledge base has this kind of a sentence, it's an implication. Alpha gives rise to beta, and there is alpha also one of the second sentence. Clearly, beta is derived, right? You know, alpha gives rise to beta, and also alpha is observed, then beta can be derived from that. This is simple. All birds can fly. Eagle is a bird. That is how we say, sorry. Birds can fly, and eagle is a bird, so obviously eagle should fly, something like that. So yeah, may not be an ideal example, but I want you to see how we can derive these things, because you have this sentence, A gives rise to B and A happens, so B has to happen, right? Something like that. And a lot of such simple to elegant algorithms are built on top of this language. So it started the knowledge-based building knowledge-based agents, right? People, oh, it's paused, is it? Okay. Sorry. Right. So I was going through some slides. Unfortunately, it was paused. The share was paused. Right. So yeah. So as I said, this language is quite fairly powerful, and it can represent knowledge and also enable algorithms to derive newer sentences from what is known already. Okay. So I'm just going through a little faster because it's too much to cover in 1 hour. Also, a lot of theory has been developed on top of it. For example, a simple algorithm which is known as forward chaining. I'll try to quickly go through. Okay, it is an inference.
May I say something, Dr. Konda Reddy?
Please, ma'am. You can
just
always
in
suggest.
case, yeah, just in case this does not complete, or you think that you are going very fast. You can, I mean, we can have small another session by you, so don't worry about it, because I mean,
No, it's
as you
only
know that participants should be equally, I mean, going with your pace. So please take your time. Don't feel that, I mean, stressed on the topics to be covered. Thank you.
Right. Yeah. So to be very honest, fairly, I mean, I didn't probably work enough on my pace. That is the only reason, except that there is no really problem actually. Yeah. So anyway, so let's try to look at one important but very simple and effective inference algorithm. Okay. So I'm not skipping anything. Taking ma'am's suggestions, I'm going through this particular algorithm because it is really simple but effective also. Okay. So let's try to see what is forward chaining. It's an algorithm. It determines if a single proposition symbol, that is a query, is entailed from what is already known or not. Okay. It can determine if a single proposition symbol or if a single statement is entailed or not. Okay. Let's try to see through an example. Okay. What it does is it starts from the known facts, all the positive literals in the KB, right? The world knowledge can be represented using simple literals that are true, and also some observed knowledge also, not only the general facts, but some observed knowledge is also represented already in KB. So from there, it starts, and if there are any implications, implication means alpha giving rise to beta, that kind of a sentence in knowledge base, right? If there are any premises, if there are any implications like that, and you observe the, so let me just quickly go to the whiteboard that kind of completes the argument. Okay, let's say my sentences are like this. I have A and I have B, and A gives rise to P, something like this. These are my sentences, sentence number 1, sentence number 3, and so on. Okay, so the algorithm it has some positive literals and it has some implications. Sorry, these are called implications. A sentence of this form is called implications because A is implying P, right? And we already know A is already observed, which is true. So it derives P and adds as the fourth sentence. Because A is there, if A is there, P should be there. So it adds P. So this forward chaining algorithm is as simple as I said. Okay. It starts from all the positive literals and goes to the implications. Wherever the premise of an implication, premise is whatever sitting on the left side of this implication is called premise, right? If it sees premise, it will add the right side of the implication to the knowledge base. That is the simple thing. If all the premises of an implication are known, the conclusion is added to the known facts. For example, it can be a complex implication also. For example, in place of this, I had A and B imply C, right? It's not a single implication. It's a complex implication where both A and B have to occur. Fortunately, both A and B are already there in my knowledge base. So if all of these things that are there in the premise are observed, then the conclusion is adding C to the known facts, right? This is forward chaining. The name itself is quite suggestive. It concludes in the forward direction by observing all the parts of the implication and concluding what is on the right side. It's very intuitive, right? So this algorithm is called forward chaining. And how does it look like? So for example, if you want to understand, so this is a little more complex knowledge graph where you have A, B. These are sentences in my knowledge graph. Okay, I'm reading bottom to top. Okay, so I have B in my knowledge graph, knowledge base, and I have A also. And one of the sentences is an implication where when A and B occur, they imply L. And similarly, A and B occur, they imply L also, and so on. B and L imply M, L and M imply P, and P implies Q. Now I want to ask the question whether I can infer Q. Okay, whether I can add Q to the knowledge base or not. So clearly, starting from atomic sentences A and B, now A and B are observed. So L can be observed. Following this sentence, L can be observed. And L and B, both of them give rise to M. So L and B, both of them give rise to M. And you see, and L and M give rise to P. So L and M give rise to P. And P give rise to Q. Clearly, P to Q. So with all this information, we can derive another new sentence, which is Q. We can add Q to the knowledge graph because these sentences clearly are inferring Q. Okay. So this is very simple forward chaining algorithm, which can run inference on the logic, the language that we have just discussed. Okay. Right. So that is what I had for, but before that, there was the clear syntax and semantics of the, let's go back to the taxonomy. I will just give you the bigger picture before we move on. Just hold on for a second. Yeah, here. So these are all different languages to encode world knowledge. What changes? The syntax and semantic changes. How granular you want to represent the world truths, world knowledge, that depends, that changes across these languages. So what we have just seen is the propositional logic. Very simple, in a way, historically also kind of very primitive, I would say, language to encode knowledge. Okay. So as I said, if you go a little more detailed about the world, like representing objects separately and relations separately, and then encode sentences using these objects and relations and all, you can go very complex with first order logic and so on. So that is one thing. So for the rest of the talk, we will talk about the other language, which is probability. How do we represent the world knowledge using probabilities? Okay, so that is this, what I am highlighting now. Is probabilistic propositional logic. Let's see how we can represent the same world knowledge using a different language of probability. So it requires some knowledge and some basics about probability, which I'll try to cover very briefly again. Right. Okay. So we need to understand uncertainty in AI, through which we can build Bayesian networks, and we can even extract inference. Similarly, the ultimate goal is to run inference from whatever knowledge that you represented. You need to derive new knowledge. You need to extract some inference. Inference means what can be inferred from these conditions? What is next best action for the agent to take towards maximizing the performance or towards achieving a task, right? That is ultimate goal, not only representing. The representation has to facilitate taking a good action for an AI agent. Okay, so that is the ultimate goal. So far, we have modeled the world very deterministically. There is either true or false. There is nothing in between. Okay, so that is quite restrictive. Real world doesn't work like that, right? There is a lot of uncertainty, a lot of randomness in the truth value. For example, lifting a cup. So you can say, I can lift a cup or I cannot lift a cup. According to the propositional logic, there are only two possibilities. I can or I cannot. But there are real world situations. Maybe it is heavy. Maybe you got confused and picked something else. So although you were able to pick, but you got confused and you picked something else. So you did not really pick, right? Or it is a showpiece. Maybe it is attached to the table very strongly. You didn't know that. So you tried and you failed, right? But obviously you could lift, but you could not lift in this particular instance. So the real world is really away from being very binary, right? So all of this has to be, the logic fails here. Logic you cannot represent very harshly like this. So that is where you need the randomness or stochasticity in having truth values for these things. Okay, for example, all ways in which a car can break down, you cannot list all these things, right? And also, for example, a person has cough and cold, and what diagnosis we need to make. You cannot say if a person has cough and cold with 100% probability, this is the disease he has. No, right? There can be multiple diseases where the symptoms are cough and cold. So with certain probability, this may be this. With certain probability, this may be other disease, etc., etc. But logic, you cannot do this. Only probability can bring in this kind of flexibility, right? There are a lot of reasons why we should go away from logic towards probability, right? I hope you are able to see the limitations of logic, the propositional logic that we have seen, and the importance or the ability of probability to represent these real world scenarios. Okay, right. So we need to make inferences in life that are not logical anymore, but they are random or stochastic in nature, right? They have some notion of likelihood. How likely is this to happen? How likely is this to happen, etc. Okay, so again, in the bigger picture, we moved from propositional logic where we only had facts and we had truth values associated with them. But now we are at this line where our language is probability theory. Although there are facts, but there is degree of belief for each of the facts associated, which is essentially the probability for those facts. Right. Sorry. As I said, probabilistic relational models, they combined probability and first order logic, etc., etc. But essentially, late 90s and early 2000s, AI was completely driven by these probabilistic models, probabilistic graphical models, and lot of other derived models that are built on top of probability ruled AI. Before actually deep learning took over and neural networks and deep learning took over, probabilistic PGMs, graphical models, were the tool for AI back in 2000s. Okay, right. So again, there are a lot of ways you can compare the logic versus probability. Essentially, you have symbols on one side, you have random variables on the other side. You have Boolean values on one side, and the random variables can take any value based on the domain. And the state of the world here is complete assignment to all the state variables is the definition of a world state. But here, there are joint probability, and there are different ways of representing the world via these random variables. We will see. All right. So I'll quickly go through again basics of probability before we actually represent some world using probability. Okay. So a set S is known as sample space, where, for example, if you throw a dice, there are 6 outcomes for the as the possibilities, and that is called sample space. The possible outcomes are sample space, and X belongs to S is a sample point or atomic event, or sometimes you call it one of the possibilities of the world. Okay, so each of the outcomes is known as sample point or atomic event. So probability space is essentially assigning probability for each of these sample points, which is basically a value between 0 and 1, and summation of all these values to be 1. And an event is defined as a subset of these sample space. For example, if you roll a die, and an event can be defined as getting a face which is less than 4, right? It can be 1 or 2 or 3. So event A is defined as any of these things is defined as event A. Okay, so any subset of sample space is defined as defined as event. And the familiar definition, random variable, is a function from the sample space to some other range, some real quantity. Okay, so you assign the each faces of these die to a real value. That can be a random variable. Okay. Okay, now let's take some example. So you visit a dentist because you sensed some toothache in the mouth and you suspect there is a cavity in one of these teeth. Okay, so cavity, whether you have cavity or you don't have cavity, it can have 2 values in propositional logic, right? You have cavity is true if you really have cavity. You have cavity is false if you don't have cavity, right? But that's about propositional logic, and the variables can take only one of the 2 variables, one of the 2 values. Discrete random variables, on the other hand, it can take a lot of possible values. It can be finite or it can be infinite also, right? For example, weather, if you want to represent the weather as a random variable, it can take one of the 4 values. It is sunny, it is rainy, or it is cloudy, or it is snowy. One of the 4 possibilities, right? It's no more binary now. And on the other hand, but it is discrete. It's kind of categories if you think of them as classes. Okay. But on the continuous random variable, it can be any real value. For example, temperature can take some real value, right? 21.6, 30.4, anything. This is continuous random variable, a little more complex than discrete random variable to understand. Okay. But we all know the axioms of probability, where probability of a true event is 1, probability of a false event is 0, and A union B probability is computed as probability of A plus probability of B minus probability of A intersection B. This is easy to see with the Venn diagram and all, right? Right. So now, what is a prior probability or unconditional probability? It corresponds to our belief prior to any other evidence, right? For example, probability of having a cavity is 0.1. Generally, we don't have a higher probability to have cavity, right? And also probability at this point in time, probability of weather to be sunny is very considerably high, 0.72, right? We are already into March, right? This is observing no evidence. We are computing or assigning probabilities to some of the events. These are unconditional probability or prior probability. These are known as prior probability. Okay, and probability distribution gives values to all possible assignments. Okay, so knowing the probabilities for all the possible values, for example, weather can take 4 values, and what are the possibilities, what are the values for all the 4, it's clearly defined by probability distribution. That is probability mass function in case of discrete variables, PMF they call it, probability distribution for real variables. Okay, now joint probability, again, for a set of random variables, it gives probability for every atomic event on those random variables. For example, let's take this example. There are 2 random variables, weather and having a cavity in my mouth. Okay, so cavity, there are only 2 values, true or false. Weather, there are 4 values, sunny, rainy, cloudy, and snowy. So in total, there are 8 combinations, right? So this row 4 values and this row 4 values. Okay. In total, the probability distribution will have 8 values representing probability for every specific value assignment. Okay. What is the probability for weather being sunny and cavity true? This quantity 0.144. Okay. So this is probability, joint probability distribution for weather and cavity random variables. Okay. So again, we are just going through the terminology, slowly building up the representation using probability. Okay. The posterior probability is probability for one random variable after you observe another thing. For example, probability to have cavity given that you are suffering from toothache should be high because you already have having pain in the mouth. Because of that, maybe there is some cavity that is what is causing the toothache. That's why you have 0.8 probability, considerably very high. New evidence sometimes may be irrelevant. For example, probability of having cavity given that you are suffering from toothache on a sunny day. The day being sunny, it's irrelevant to have a cavity or not to have a cavity, right? But on the other hand, having a toothache has clearly some influence on having a cavity or not. So that event is independent of being sunny day. So that you can write as probability of cavity given toothache and sunny is only probability of having cavity given toothache. Sunny is independent of being a sunny day or a snowy day, etc. Okay. So this is called conditional probability, and this is you can see independence also between sunny, right, and cavity. So this is typically one way to visualize conditional probability, where probability of A given B is represented as probability of A intersection B by probability of B. Okay, right? So this intersection region is represented here, and that becomes of your interest given that B is observed. So you will be focusing on only this part of A. Okay, right. So the very important rule in probabilistic inference is this chain rule. Okay, so let's try to understand this fundamental chain rule. Probability of all these random variables x1 to xn can be decomposed as this: probability of xn given 1 to n minus 1, xn minus 1 given 1 to n minus 2, and so on. You can go on decreasing and you will essentially end up with probability of x1. Okay, so how did we come up with this thing? So the same formula, probability of A given B is equal to probability of A intersection B by probability of B. So if you start from the first term, so it will have probability of xn intersection 1, 2, and so on n minus 1, which is what we already have on the left side, divided by the bottom, right? Probability of B, which is x1 to xn minus 1. And if you do the same for all the terms, you will essentially end up with the left hand side. Okay, so that is how you prove this. It's a very simple thing, right? So essentially it's a product of a lot of conditional terms: xi on 1 to n minus 1, x2 on 1 to n minus 2, and so on. Okay, so please keep this in mind. This will come very, very handy in later discussions, right? So independence, as I said, probability of A given B, if at all, if it is equal to probability of A, you say, and also you need to have this also, probability of B given A is equal to B. That means observing B is not really changing my probability of A. Similarly, observing A, so whatever that we write on right side of this slant is given. That means that we observed, right? And if it is not changing the probability value of B, then they are independent, right? So as we said, having a sunny day doesn't really affect having a cavity in my teeth, right? You can think of other examples that are kind of orthogonal, which cannot really influence, right? So then you can realize independence. It's a powerful concept, but it doesn't really hold in so many practical applications. Okay, but on the other hand, conditional independence can be more practical than complete independence. So conditional independence is like this: probability of catching a cavity. Catching a cavity means if you go to a dentist, he will probe for some microorganism in your mouth, essentially that are result of having a cavity. If there is a cavity, these microbes will go and then live there and thrive there, right? So they will probe for microbes. If they catch, that means you have cavity, right? So probability of catching this microorganism, given that there is a cavity and toothache, is equal to probability of catching given cavity. If cavity is there, independent of toothache, you will anyway be able to catch the microorganism, right? Some people have more threshold for toothache. Some people have less threshold for toothache. It doesn't matter. As long as there is cavity, there is high probability for catching, right? So that is what is conditional independence. Conditioned on the cavity, catching is independent of toothache, right? So you can think of a lot of other such things. One of the random variables is the reason. So the rest of them will not really affect. So that way, this becomes independent. Catch is independent of toothache, conditioned on cavity. Okay, so this is more practical and more useful also in practice. And because it reduces the storage complexity, we will see how it reduces also. So a lot of useful properties are there for this conditional independence, which are being explored in Bayesian networks. Okay, right. So where we are going on this probability theory is basically we want to have this joint distribution where we can answer any queries. Why do we need to answer any queries? Recollect, we were querying whether the Wumpus can move to one of the adjacent cells, right? So there we expected either true or false as the answer from the KB, from the knowledge base, so that we can go or avoid going. Here, with all the information about the world, you want to understand the probability for taking an action. That can be a query, right? So if at all you get a convincing probability, you take or you don't take the action, right? That is the idea. Why all this painful probability that we are doing is to build the joint probability that binds all the involved parameters, which are random variables in our probability language. Okay, so now we bind all of them using this joint distribution, and we now ask questions. What is the probability for this to happen? And then based on that, the AI agent will take an action or will not take an action. And you need to have a mechanism to answer those queries. That is exactly where we are going. Okay, now let's take another example. Mr. Bean goes to a dentist, and this is what is observed. Okay, so there are three random variables. Three random variables, which is catching a microorganism, or having toothache, or having cavity. Okay, so now let's take a look at this joint distribution. If at all there is a toothache and there is cavity, the probability for having for catching the microorganism is 0.1. For not catching is less, because there is cavity. You will essentially will be finding, right? So not catching is 0.012. Okay, these are some probabilities. Try to understand each of the meaning. So when there is toothache and there is no cavity, what is the probability to catch microorganism? Microorganism is more dependent on having cavity or not having cavity. If there is no cavity, it is very less likely to catch, right? Cavity, microorganism thrives on cavity. So if there is no cavity, it's less likely. That is why it is 0.016, right? So which of these quantities would be very strong? For example, there is no toothache, there is no cavity. What would be probability to not catch organism? Because there is no toothache, there is no cavity. Obviously, you are healthy. There is no toothache, there is no cavity. Obviously, you're very, very healthy. That is why the probability for not catching the microorganism is 0.576, right? So now, with this kind of a PMF, you can ask any question and get an answer. For example, I'll ask some question. What is the probability for toothache? If this PMF is there in the knowledge base of a AI agent, we'll talk about deriving these values. First of all, I want you to understand what is the use of this joint probability distribution. Okay, if at all I have this, I can ask questions and get my answers. For example, I can ask, what is the probability for toothache? Now, can somebody tell me which values I should add? Right. Okay, I'll just go ahead. First 4, because the toothache, this column, which has 2 sub columns, all of them you have to marginalize to get probability of toothache. Okay, so whether you caught or you didn't catch the microorganism, it doesn't matter. So all the four, yes, you're right. Yeah, so all these highlighted in blue, if you add, it will give the probability for toothache. So based on this probability, you can take an action. You can understand what is the thing. Okay, now let's what is the probability that Mr. Bean has toothache or cavity? Okay, now I ask this question. What is the probability that Mr. Bean has toothache or cavity? So toothache is here, cavity is here. Okay, so one random variable is this and another random variable is this. Okay, so what do? Probability of A union B. It has to be probability of A, probability of B minus probability of A intersection B. Okay, whatever I'm highlighting, you need to add it only once. Okay, if you add all of these highlighted ones, you will get 0.028. So that is how you compute probability of toothache or cavity. And another question, probability of not having cavity given toothache. So we know that there is toothache, sorry. We know that there is toothache. Now you want to understand, is it because of the cavity or not because of the cavity, right? So this is performing inference. We understood that Mr. Bean has toothache. Now, is it because of the cavity or is it not because of the cavity? You need to understand that. Okay, so you can do all these questions. Because this is a conditional probability, you can look at this as probability of A given B. How do you compute? Probability of A intersection B divided by probability of B. Okay, so the toothache, this red one will become the denominator and the green one will become the numerator. Not cavity, intersection toothache. So NAT cavity is this row, intersection with toothache is these two. You sum these two divided by the entire sum of the red box. That will give you 0.4. That means given that he has toothache, this is 0.4 probability for not having cavity. The toothache is because of something else. Okay, so this is some inference. So you can tell whether it is because of the cavity or not because of the cavity. Okay, so because it will be some inference the AI agent wanted to perform. Okay, so all this you can perform. The ultimate aim is to understand or have this kind of a probability density function or distribution, joint distribution. But it is really complex. You with more random variables, because real world will have a lot of parameters. The AI agent should look at multiple such things, whichever is important, whichever can affect the decision making. If you include all of them, the complexity will be exponential in the number of the domain values of each random variable. Okay, so because of that, it's really difficult, although it is possible, but it's complex. So this is where we exploit independence, where we can among these random variables, if at all there is independence, we can exploit and make it less complex. For example, take a look at this thing. There are 4 random variables: whether having toothache, having cavity, or catching the microorganism using a probe. Clearly, some of them are dependent, some of them are independent. So if at all I want to represent all these entries, all these random variables, how many entries will be there in the joint distribution? Weather has 4 variables and the rest of the 3 will have 2 each. Obviously, 4 times 2 times 2 times 2, 32. Okay, now I know I can decompose this into like this. There are 3 random variables that are dependent and that are independent from the 4th one, weather. Okay, now can you tell me how many? Because this, you can look at the equation. Probability of these 4 random variables, because of the independence, you can represent Nayan. It's wrong. What you said is wrong. Can you please think again? Look at the right hand side equation. Now, how many entries will be there? So look at the first part. The first part, toothache, catch, cavity. How many entries will be there in this? The first part, how many entries will be there? Toothache, catch, cavity. 2 each, right? 8. And weather? No, it's not 6, because each of them will have 2 raised to 3, 8 will be there. And the weather, how many values you need to how many entries you need to represent the weather, probability of weather? No, weather has 4. No, weather has sunny, rainy, snowy, and cloudy. 4 of them. 8 plus 4, it will become 12. From 32, you came to 12. Okay, so this is possible only because of the independence. So again, complete independence may not hold often. So conditional independence is what we rely on. So the one question, joint probability distribution used to correlate two variables. If multiple variables having high correlation, which need to take into account. So that is what is happening, Vijay. So for example, out of 4, 3 of them are correlated. They are not independent. So you need to have that relation, that binding together, which is, if at all there is independence, that is ideal because the entries are getting smaller. So you can represent the world very easily. But real world nature is like that. They are dependent. So we cannot really make them independent. If we make them independent, we are making costly assumptions. Your accuracy of inferences will go down. So you have to respect the physical dependency and try to model within the complexity. Okay, right. So conditional independence, we have seen some of the random variables do not really depend on some of them. For example, catching microorganism depends only on having cavity or not having cavity. Toothache may not be dependent because, as I said, microbe and toothache, microbe and cavity are related. When there is a cavity, you will see some microorganism growing there. That is where you probe and find. Okay, so these kind of conditional things can reduce the entries in the joint distribution. Again, you try to work out how 7 becomes 5. If you just try to express the joint distribution as the chain rule, you would be able to understand very easily. Okay, the chain rule has to be utilized to exploit this conditional independence. You need to split to exploit the conditional independence. Only then you will be able to save the entries. Okay, so this also is a small example. You will be able to understand if you just expand the conditional independence. So another important thing in the language of probability to represent world knowledge is Bayes' rule. So again, this is kind of a fundamental. So this is how it looks like. Probability of x given y, typically known as posterior, is expressed as likelihood times prior divided by evidence. So generally what happens is probability of effect given cause is very easy to find. For example, what I am highlighting here, probability of effect given cause. So what is the probability to observe high temperature when you have fever? It's very easy, right? When you have fever, obviously we know that the temperature rises. So it's very highly it's high value. It's easy to measure also. But on the other hand, probability of cause given effect, right? So what is the probability of fever having high temperature observed? The effect is having high temperature. The cause, the reason behind it is having fever. So this is going the other way, not the natural way. So this is what typically you want to find out. And because it is difficult, we use Bayes' rule to get back to the comfortable form. Probability of effect given cause times probability cause divided by the effect. This is a normalizing factor. This need not be computed also. You can normalize it and then get ahead. Right. So I want you to understand the Bayes' rule can be exploited whenever you need to have this kind of an inference by the AI agent. So this is easily available and things can be computed comfortably on the right side. That is why you go to apply this thing more often. So this theory, what we have been discussing so far, and the Bayesian networks and representing the world dependencies, etc., led to the Nobel Prize in Computer Science, which is Turing Award for Julia Pearl for developing all this theory of probabilistic models. So, for example, so I'm just representing the same thing using multiple slides. Okay, so for example, how to represent this dependency, right? Cavity leads to catching microorganism, because cavity is the reason for the microorganism to grow, right? If there is cavity, it will lead to microorganism and it will lead to catching of the microorganism. Cavity also leads to toothache, because it's a damage to the teeth, you will feel toothache. So this is the dependency among the random variables, 3 random variables. Representing this kind of dependencies is what Bayesian network does, right? So this is another language to represent world knowledge. What is the knowledge here? Cavity leads to catching, cavity leads to toothache. But there are not certainties, there are probabilities for this to happen. That is where probability comes into picture. Again, try to correlate what we have done in the first half, where we try to represent using truth values and knowledge base, etc. Now here the knowledge base is a graph. It's a network, directed acyclic graph, where each of random variables is linked through some dependencies. And again, this leads to is also not certainty. There is a probability for everything to be realized, right? So that is the bigger picture. Okay, so this is exactly what probabilistic inference means in the context of AI, representing the world with uncertainty also encoded in the probabilities. Okay, so one example is like this: probability of cavity given toothache and catch. So the AI agent observed toothache and also observed microorganism, right? What is the probability for cavity? Try to recollect. The cause is cavity, effect is having toothache and catch. This is difficult, right? So you go the other way around by applying Bayes rule. Cavity leads to toothache. That we already know, or we generally tend to measure these kind of things more often, right? So you convert it using the Bayes rule into this, and also meanwhile you exploit the conditional independences also. And obviously you will have the PMF to help you to compute all these things. And AI agent will know what is the probability for this event. And based on that, it will either take action or not take action. Basically, to understand is where we are going. Okay. Again, so exploiting conditional independence will reduce the complexity of representing all these tables of probability, which is joint distribution. Okay. So roughly it is linear. If you have conditional independences, you will have 2n plus 1, where n is the number of such dependent random variables. Okay. All right. As I said, syntax is the graph. You have like this. For example, to end the session, I'll end with one example. How do you actually represent the world using probabilities, and then perform some inferences? Let's take a simple example. You are living in some colony. Your neighbors are John and Mary. You went to a party. One of these days you went to a party, and you are just enjoying there. And you already informed John and Mary that if there is an alarm in your home, you just give me a call. Okay, so that is what you informed John and Mary, right? So generally your alarm goes off. Alarm rings when there is a burglary. When somebody intrudes your house, there is an alarm. Or sometimes earthquake also happens, because of that alarm rings. These are the two reasons for alarm to set. When there is an alarm, one of your neighbors, generally you told John to call, and also other neighbor, left side neighbor, Mary also you told to call. So they oblige, not every time. Okay, so because they have their own lives, right? They may not be there in the home. They may not have heard about the alarm. If at all they heard about the alarm, they also willing to help you, only then they will call. So there is a probability for every event. It's not certainty. But typically the dependencies are like that. When there is a burglary, your alarm rings. When there is an earthquake, your alarm rings. Again, not certainty. There is some probability with which alarm will ring. Okay. Some cases, even burglary may not give an alarm, because burglars are even intelligent these days. Some of these burglars will set your alarm off and then enter your house. So there is a probability for every event. So this you want to encode. How do we do that? So this is how you do that. Just I'm exploiting the same thing, but in detail, the slides will explain you clearly. So this is the dependency network. Earthquake may lead to alarm. Burglary may lead to alarm with, again, probabilities, not certainties. And when there is an alarm, John may call you, or Mary also may call you. Again, not certainty. There is probability. The world is probabilistic, right? This is more general. If you feel that is certainty, assign close to 1 probability. That is a possible event. Even in the probabilistic world, you can have closer to 1 probability to represent certain events. Okay, this is more general, right? With this kind of a thing and exploiting the independence, conditional independence and all, so you can clearly have the probability distribution simplified. For example, let's look at this conditional joint distribution. Probably, how many random variables are there? There are 5 random variables: earthquake, burglary, alarm, John calling you, Mary calling you. 5, right? The joint probability of all of them, you write the chain rule and try to exploit the conditional independence, right? So alarm depends only on earthquake and burglary, not the other 2, right? John depends only on the alarm. Mary only depends on alarm. How do we know that? That is the knowledge about the world. You told John to call if there is an alarm. You told Mary to call only if there is an alarm, right? So all these things can be exploited to simplify the terms in the joint distribution. And you can perform inference also. You can ask any question now. For example, you can ask, given the alarm is set off, is John calling independent of earthquake? Okay, given that alarm rang, John calling you, is it independent of earthquake happening or not? Right? Can somebody answer this question? This is the real world represented using Bayesian network. Given alarm rang, is the event John calling independent of earthquake or not? Independent. Yeah, multiple people said independent, because anyway, earthquake may lead to alarm, right? Having known that alarm occurred, John anyway will call you, right? Knowing earthquake happened additionally may not change the probability for John to call. John calls if there is an alarm, right? Knowing that earthquake occurred or not, it doesn't really matter. John calls when there is an alarm. Okay, so that is how you can, because again, it's an easy example and also it's easy and meaningful. You are able to infer very easily, but think of complex world with multiple random variables and possibilities and complex dependencies. Everything needs to be captured by Bayesian networks, which is a graph like this, directional acyclic graph like this. Once you have this thing, you can perform, there is theory again, the computer science Nobel Prize, which is the Turing Award, is because of the theory developed to facilitate inferring on these kind of Bayesian networks. Okay, so there are some important theorems which are simple enough and very intuitive also, which dependencies can be independent and all that. So again, in the interest of time, and also this is really ambitious to cover in 1 hour, at least my goal is to make you understand probability is one of the languages to represent real world for an AI agent. Why? Based on which it can take actions. It can take inferences. It can understand what is the best action, what is more likely to take, what action is more rewardious, right? So I hope that is the goal of this exercise. Starting with the propositional logic, we have seen one language to represent real world knowledge, and also perform inference on top of it. Knowing to represent is one thing, and exploiting the represented knowledge to perform actions is another thing. That is where the inference algorithm comes into picture, right? Here also, representing the world knowledge in Bayesian network. Bayesian network is an acyclic directed graph where you can clearly see dependencies among the random variables. That is one thing. And exploiting independence, conditional independence, and answering queries is another part of it, which is what we have just seen, right? So how do we actually compute different probabilities given this kind of information? So that is performing inference on Bayesian networks. lot of theory has been developed, approximate, exact ways of finding out these probabilities and taking an action based on them is a big theory, a semester level course on itself, probabilistic graphical models, right? All right, so I'll try to stop here. I think I have summarized enough, and also I have convinced that these are something that really have driven AI during some phases in the history of AI, right? Starting from its inception all the way before we discuss the recent advances, which are deep neural networks, all the way to transformers. This is how the field evolved, starting from the very simple logic and using probability as a language to represent and take actions. And we will see further what happened. All right. I'm really sorry to break the time contract.
No, in fact, we gave you a very tough task of
Right.
doing it in this 2 hours, which was really difficult, and you have managed it so well. I must say that
Thank you.
it was such a wonderful, lucid presentation and explanation of various concepts, which are like, I remember my teacher used to tell that a good mathematician is one who makes difficult things look simple.
Yeah, he's right.
And that is the quality of a good teacher as well. So I'm really so much amazed to see how you have covered in such a short span of time. Thank you so very much. Your lecture was so good. I really enjoyed each and every part of it.
Thank you, ma'am. Thank you very much. It means a lot to me.
Yes, and participants have been asking questions to you, so that shows that they were all the time very much keen to know what you're telling. Very interesting presentation and lecture. Thank you so very much. On behalf of Asia Connect project coordinators, Dr. Professor Preeti Khanna and myself, I sincerely thank you, and hope to receive your support in future as well.
Sure, ma'am. Sure, I'll be more than happy.
Thank you so very much.
Thank you.
And participants, we will be meeting at 6. So have a little rest, have a cup of tea and coffee with your family and friends, and then please join us again at 6 p.m. before 6 p.m. so that we can start sharp at 6 p.m. Thank you so very much. And we are meeting soon. Thank you.